Welcome to my channel. Let's have a look at problem 685, redundant connection 2 together. So for this problem and in this video, we are going to share a solution using breadth first search plus in-degree. I'll first read through the statement of the problem, then analyze the method and the examples, and then we share the code and do the case test. So first, let's look at the statement of the problem. In this problem, a rooted tree is a directed graph such that there is exactly one node, called the root, for which all the other nodes are descendants of this node, plus every node has exactly one parent, except the root node, which has no parents. The given input is a directed graph that started as a rooted tree with n nodes, with distinct values from 1 to n, with one additional directed edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge that already existed. The resulting graph is given as a 2D array of edges. So each element of edges is a pair like UI, VI, that represents a directed edge connecting those UI and VI, where UI is a parent of the child VI. In other words, the parent UI points to the child VI. So in this problem, we are required to return an edge that can be removed so that the resulting graph is a rooted tree of n nodes. If there are multiple answers, we are required to return the answer that occurs last in the given 2D array. So that's the main statement of the problem. So let's look at the examples. So in example 1, there's no directed cycle. However, the node 3 has two parents, that is 1 and 2, right? So the output is 2, 3 here. And in example 2, there is a directed cycle starting from 1, then traverse 2, 3, 4, then come back to 1. So actually in the directed setting, there's another possibility, for example, which involves multiple parents and directed cycle together. For example, in example 2, if we revert the direction of edge 1, 5, we get 5 point to 1. So 1 has two parents, 4 and 5, and at the same time it evolves to the directed cycle. So that's another possibility, right? So that's the analysis of the examples. So now let's look at the constraints. So for this problem, the length of the edges is not that long, so it's bounded above by 1000. So this actually has some hint or provides room for doing a more intuitive method here. And lastly, UI does not equal to VI for each edge. In other words, there is no self-cycle. So with that said, let's look at the method here we're going to use. Here we're going to use a very direct or intuitive or brute force method. We use breadth first search plus in-degree. So this is sort of very straightforward. The idea is as follows. So we look at the edges array from back to front. In other words, we do it in the reverse direction, and then we remove the corresponding edge and check if after removing the edge we can traverse all the nodes from root. So if so, it means that we get a valid tree. So the graph currently, the edge we're looking at, so it's the one we're going to return. So if not, we continue to examine the other edge remove it, and check if from there we can traverse all the nodes from the root. So that's the method we are going to use. Here, let me first do some briefing. So for the concept of in-degree. So in a directed graph, the in-degree of a node is nothing but the number of distinct directed edges ending at I. So that's the in-degree. For example, in example 1, the node 3 has in-degree 2. Node 1 has in-degree 0, therefore it's the root. And node 2 have in-degree 1, right? So that's some examples. So for the in-degree application, so I actually, it directly pops to my mind that, so for example, when we do topological sort, so for example, in Kahn's algorithm, we use this in-degree. So you can also encourage to look at the cost schedule problem. And so they used they required to, one solution is to do topological sort and using Kahn's algorithm, which involves in-degree. So that's the in-degree. And I also want to comment on unified. So for unified, we can use the unified to solve this problem. However, so we need to consider the different cases like multiple parents, directed cycle, and the mix of these two. So in other words, we need extra logic. So actually, we also have tried this method, so it works. And for me here, I guess the breadth first plus in-degree method is more intuitive, especially in view of the small number of nodes. I'll try to present the BFS plus in-degree method, which is more straightforward in my thought. So let's do this code now. For this, I'm going to write a hyperfunction which basically does a traversal from the root and to check if it can finish the traversal to get n nodes. So that's a Boolean function. So the main function basically runs the idea here. So for this carry out the whole procedure, let me first track the length information, so edges. So n is the length of the edges, right? So it's also the number of nodes. So also we want to first initialize a graph just for preparation. So I'm going to use node set representation of graph. So here for I in range m. So here the nodes is from 1 to n. Also the in degree. So we are going to set it as 0 at the very beginning. So for I in range m. So with this preparation, I guess let's first build the graph. So build the redundant graph from the edges. So for AB in edges. So graph A at B. So here it means B is a neighborhood of A, or B is a descendant of A. In other words, we mimic that A points to B directly. So also we want to get the in-degree information for B, because A is in the direct edge from pointing B. So we want to increment the in-degree of B by 1. So with that said, let's stop here and then write the utility function or hyperfunction. So we can actually write the function instead or below this main function, but in order to make it decoupled, I will write as a method. So I'll call it found all. This is essentially a traversal. So first it accepts the graph. We need to traverse the graph. We need to know the in-degree information, and also we need to know how many nodes we have. So that's the arguments or function signature. So now we do the breadth first search. So for this is very routine. So we're going to initialize a set, trying to monitor the nodes we have visited. And also we need to use a queue. So here I'm going to use a deck. So let me do a call this from collections import deck. So then we have this deck. Basically, we use it as a queue for breadth first search. And then first, I want to check if there is an edge with 0 in degree. That edge, that node will serve as the root. So for I in a range 1 n plus 1. So what we want to do is that we check the in degree of I. If in degree I equals 0 or not. If it equals 0, it means it's an root. So we're going to append that one to the queue. This is the process. So afterwards, here actually we can use early stopping. So if we add it, so we are going to break. So yeah, if we are worrying about the other things, like if there's a multiple nodes with 0 in degree, that's also a possibility in a strict sense. But yeah, we can comment out if we like. So finally, we want to check if length of the queue equals 1 or not. If it equals 1, it means that we have the unique root. That's good case. So otherwise, so if it's not equals to 1, so we're going to return false. In other words, so we cannot do the full traversal, right? So actually here are two possibilities. If the length is 0, in other words, there's no valid root. So, or if the length is greater than 1, so it means that there are multi-roots. That's also impossible to finish the traversal. With that said, let me do initialize a variable called found. So found is 0 at the very beginning, which basically monitoring how many nodes we can traverse starting from the root we found in the scan here, linear scan here. So then the next is the basic traversal or while loop. So we're looking at the node. So here we queue pop left because we are using it as a queue, and then we are going to increment the font by 1 and add the font to the node to the set. So after that, what we are going to do is to traverse the neighborhood of this node. So for x in graph this node, then I want to check if x is visited or not. If x not in visited, so we're going to append this guy, append x to the queue. So otherwise, it means the edge from the node to x is already is redundant, right? Because we already visited the x, so we are going to return false. So in other words, we are not we have cycles. We cannot make the full traversal. So otherwise, we're going to return in the final if the number of found nodes equals n or not, the total number of nodes. So if so, we can finish the traversal. So that's about the breadth first search function. So now let's come back to our main function. So what we want to do is that we do this from the examine the edges from the reverse direction for edge in range. So let's see, for I in range, so n minus 1, so we are ending at 0, so we use -1 here with decrement 1. So we're going to examine the current edge, edges I. So what we want to do is that we remove this edge from the graph and check if we can do the BFS traversal for the full tree, if so, for the full graph. If so, the edge is the one we're going to return. Otherwise, we continue the procedure. So we move this edge. So remove B. Correspondingly, we are going to update the degree of B by decrement 1. So then we're going to check call this find all function. So for the graph, we're going to traverse for the in degree and for the n. So if we can traverse the graph, so this AB is the edge we're going to return. So we just return AB. So otherwise, what should we do? We add back the edge and then recover the in degree of B, and then continue to do the same thing. So actually, after this one, there must be something returned. So maybe we can write something like -1, but it's not necessary. So here we remove and then we add back. So this has a flavor like backtracking. So overall, that's the full code for this problem. Let's first do a special case check, then do the generic case check. Oh yeah, it passes the first example. Why not do the check for the second example? It passes the second one. So now let's do the generic case check. It passes the generic case. So yeah, I guess for this problem, so the method we are using here is brute force or straightforward breadth first search plus in degree method. So the idea is that we traverse the edges from the back to the front, and then we remove one edge and then check if we can traverse all the graph. If so, we located that edge and return that edge, and then we continue to do this thing. So that's basically about it for this problem. If we want to analyze the temp complexity, it's also easy because the find all function is an algorithm of O n. N is the edges of, or n is the number of nodes in the graph. And for this one, basically for each edge, we do such a traversal, right? So you multiply them together, you get the temp complexity. So I guess for this problem, this provides one solution for the current problem. You are encouraged to try solving this problem by unifying plus the actual logic, or you can try to solve the problem cost schedule using Kahn's algorithm to practice the in degree application. So with that said, I guess that's about it for this problem. Thank you very much.